All right, so let's get right into magnetic coupling. We're going to talk about what it is, why it occurs, and then we'll get into a derivation of the important parameters for magnetic coupling and circuits that have magnetic coupling. So what is magnetic coupling? It's important to note what coupling means to begin with. So two things that are coupled, basically the behavior of the one thing affects the other thing. So if I have, a resistor here and I have another resistor here and I connect a voltage source to this one, of course we know that a current's going to flow in this one, but nothing's going to happen to the one that's sitting over here because it's not connected or it's not coupled to this circuit in any way. Okay? But if I draw or connect two wires to this other resistor, now that resistor is electrically coupled to the circuit, and it will now the rest of the circuit will influence this resistor. I'll get current flowing in this resistor as well, and the current that was originally flowing in the first resistor will decrease because now I have another path for current to flow. Okay, well, I guess it depends on, how much resistance I add here, because if this was, Anyways, the point is adding another resistor here, if I have no wires here, it's not electrically coupled to the circuit. Once I connect wires, it becomes electrically coupled. That is not the same thing as magnetic coupling, but this is just to demonstrate what it means to couple, or for two things to be coupled. Just means that one influences the behavior of one influences the behavior of the other. In the case where there's no wires here, that is not the case because there is no way for the behavior over here to influence the behavior of anything happening in this resistor. So magnetic coupling is different from electrical coupling, okay, in the sense that it is wireless, okay? So when I have current, Ampere's law basically tells us that if I have current flowing through this coil, I am going to get a magnetic field, like I said earlier, that's going to form, around this wire here. And if I add the effects of all of those, I get these magnetic field lines that sum together, and I get these larger magnetic fields. I can create an electromagnet and create a large magnetic field by adding turns or by, decreasing the width or the distance between these turns and increasing this area. That's all what we saw here with this equation for the inductor, right? All the different ways that we can increase the inductance of this coil. Okay, if I have more current flowing, Ampere's law basically tells us I have a larger or more intense magnetic field. And Gauss's law tells us that these magnetic field lines actually form closed loops, okay? So they come back around and they form closed loops. That's important for knowing what's going to happen outside of the coil. Basically, once I get away from the coil that I'm interested in, which is this one, what happens if these magnetic field lines interact with something else or cross paths with something else, for instance, another coil? And that's exactly what we have going on in this picture. So I'm going to draw these magnetic field lines, and you'll notice that they intersect this other coil here that's completely unconnected from this first coil. Okay, so let's just call this one L1, and this one we'll call L2. So let's say L1 is connected to a circuit, and that's why it has current flowing into it, I1, or we can call it IL1 if you want. And this other coil here is completely disconnected from a circuit, so it's just standing all by itself. Well, let me draw the other field line here. Okay, and so this is what we have going on outside of our L1. We have these magnetic field lines that sort of penetrate the space that L2 takes up. And this effect of this magnetic field is that it can give rise to another current that's going to flow in this other coil. Okay, if I want the magnetic field lines to be consistent, then the current would have to flow in this direction through my coil. But this is what magnetic coupling is. Basically means that current flowing in one coil, right? Current flowing in one coil induces a current flowing in the other coil. Of course, there would be no current if this second inductor isn't connected to a circuit. But let's just imagine it's connected to a resistor and it creates a closed loop. Then current would certainly flow in this inductor while current's flowing in the first inductor. That is what magnetic coupling is. It's basically the concept that current flow, again, I'm just repeating myself at this point, but current flowing in one coil induces a current flowing in another coil. Or if there was no resistor here and this was just an open circuit, it would induce a voltage across this second coil. And so this wireless coupling occurs just by the magnetic field lines that are in the air in proximity to this coil with current flowing through it. Okay, so we can see that this could be bad potentially. If I have a circuit where I have an inductor here and I have another inductor here, and I don't want these two coils to interact with one another, I need to make sure that they're spaced and oriented such that the magnetic field lines that are coming in and out of this one, right, aren't going to interfere with the magnetic field lines that are coming in and out of this one. Otherwise, I'm going to get different impedances and different currents flowing that don't make sense anymore, because we're thinking, oh, I should have, these two inductors in series, but I might actually have some mutual inductance that's happening between the two of them if I don't account for this magnetic coupling. And so what we're going to learn in this module is basically how to account for this magnetic coupling in our circuits. It has to do with how the coils are oriented. It has to do with the size of the coils. It has to do with how the coils are wound. But we're going to abstract away a lot of those details, and we're going to look at the dot convention, which I talked about previously. And we're going to look at how to solve these circuits, how to model the induced current, and how to model the induced voltage when two coils are in close proximity to each other using something called the mutual inductance. And this is for the unintentional case. This is when two coils are coupled unintentionally, and we just need to account for the effects of that. And then when we get into transformers, that's going to be a sort of intentional coupling where we want to utilize this fact to actually basically create isolation between two circuits, but we can couple the voltage in one coil over to the voltage of another coil wirelessly, which is really unique, really interesting, and really useful. And then we're going to explore the practical implications of all of this. Okay, so I'm going to go ahead and end this video. I'm sure that I've sort of over-explained this, but if you have questions, feel free to ask. These topics are confusing, and I want to make sure everybody has a good grasp on all this stuff before we get to the final. So I'm going to go ahead and end this video, and let's see, what are we covering in the next video? Looks like we're going to start deriving the mutual inductance and start talking about how we can basically implement a strategy for solving circuits that have magnetic coupling effects. Okay, so I'm going to go ahead and end this video right here.